So I just wanted to quickly implement a shell in Python with you. And the idea here is to really illustrate the ideas behind the execute, fork, and wait system calls. So right now I only have a very basic shell, and this will be in Python. Usually they're in C, but we all understand Python better, and so we can do it in Python as well. So currently the shell doesn't do anything very exciting. We can just execute it by running python 3 shell.py, and I mean, this is an infinite loop. Like, nothing very interesting is happening. So the very first thing I'm going to want to do is actually get user input. In Python, we just get that from the input method. Now, we're almost there in terms of like getting the input. This is not very exciting right now. It doesn't infinite loop, but it doesn't really do anything well. So the last thing I'm going to do is actually add a prompt and just add this $space prompt. And it's surprising just how much this actually starts to feel like a shell already. It doesn't do anything, but it does start to feel like a shell. And we're going to exit out of that. The other thing that I'm going to do, and this is mostly going to be for convenience, is I'm going to check if the user typed exit. If the user typed exit, I just want to break out of this infinite loop. They will avoid me just continuously having to force the Python program to crash. And so now I can go in, do my commands, whatever, and then type exit, and it does cleanly just exit. Now once we've done that, we actually need to start doing something with the input that we have. If we remember from the Unix paper, they actually separate out each argument, each word, into its own sort of like element into a list. In Python, this is relatively easy to do, and my tokens is just going to be user input. And the way I split them on whitespace is just by using split. Split's default arguments will make it such that it will just split on whitespace. And just to convince you that this is actually working, I can print the tokens immediately after. So let's run this shell again. If I run ls, it does just return ls. If I want to ls home nibber, it will just split it into ls home nibber. So we're getting really close to actually having something useful. The last thing that we would need to do a priori would be to actually execute it. Python has a bunch of modules that would allow you to do this, but we're actually going to use the functionality that the OS gives us. And so in this case, we're going to do the exec function call, the exec system call. Exec doesn't actually exist as a system call. We're going to use exec v. And what exec v does is it just takes a variable number of arguments, which is exactly what we want for a shell. We don't quite know how many arguments we're going to give it. The first argument will just be the file name, and that's going to be the very first thing we specify. And then the rest of the arguments are going to be, and the actual argument list will be everything after. And so this will actually, in Python, even for a one-element list, correctly just return the rest of the list, in this case an empty list. This code doesn't work, but we'll talk more about why in just a second. So I can do python shell.py, and then I can run ls home nibber, and it fails in a weird way. But, well, first of all, because I got my variable names wrong. Let's fix that. Let's try again. So I can ls a directory, and it does the splitting properly, but it can't find no such file directory. It can't find ls. And the reason is that there is no ls within my directory. And that's where it looks for by default. In operating systems, or at least in Bash, we'll actually have a variable in our environment called path, which will be all of the directories that the shell will check to see if the command exists. So it will first check ls, and then it will check a bunch of different directories. You can see leftovers from 6004 and maybe 6031 with Java in there. It'll just check a bunch of different locations. We can get away with not using that by just explicitly specifying the location of ls, which is /bin/ls. And then we can ask it to list a directory. And that actually almost does what we want it to. Does it do what it doesn't quite do what we want to do. It ls's the current directory. Shell.py is in our current directory. So somehow we asked it to ls home nibber, and it just lsing the current directory. The reason why, and this is subtle, is that in Unix, by convention, the 0th argument is actually the program name itself. And so we actually need to give, as arguments to ls, the 0th argument will be ls. The next one will actually be the argument that it's going to use. So I fixed that by just giving it the entire tokens list. And so if we run this now, /bin/ls, and then I can ask it for /home/nibber, it actually lists my home directory. This is really exciting. It's getting really close to a shell. There's a few things I want to fix, though. I do actually really like having the path variable, and it's kind of annoying to have to print, to put bin before it every time. So I could just put /bin/ into Python. And this would in fact work. ls home nibber would in fact ls the right thing. You can also just ls our current directory, and it does do the right thing. However, there's also a system call that just looks at the path for us. We just have to add the p for path to the exec call, and then the operating system will do the hard work of going through the path, checking if the files exist. And that's just a nice thing. And so now we can really just use ls as we would normally use ls. We can ls anything, we can ls root. It really works. This is cool. There's a few more problems that are left with this. I can't run multiple commands, right? If I want to ls, and then for some reason I want to like read the file, cat shell.py, that works, but I have to keep relaunching the shell. The reason this is happening is that exec isn't a function call that returns. It's a system call. This isn't some nice little quaint system call that returns. It's a really violent process. What ends up happening here is that the entire Python3 shell.py program gets entirely destroyed and entirely replaced with whatever command we're doing. That's what exec does. It completely transforms it. And so when we run our shell and then do ls, our Python3 shell.py becomes ls. ls then prints out what it needs to, terminates, and our program has terminated. So we don't want that to happen. What we do want to happen is it to live in its own processing and the shell process not being affected. The way we do this is by using the fork system call. And the fork system call will suddenly fork our process. And forking a process means that it will make two identical copies of Python3 shell.py. And fork actually returns a little bit of something. And so let's just look at what that is. I'm going to print fork ID. This is a really good point to pause and just think about what will happen when I run ls. What do you expect to print? What is fork ID going to be? We know it's probably going to be process ID. How many of them are going to be on the screen? What's going to happen? So here's what happened. Shell.py got printed twice, one over here and one over here. And there were two fork IDs that were printed. For the parent, fork returns the process ID. In the child, identical copy of the Python3 shell.py, but they don't share anything, right? All the variables are unique, everything's unique. They're just identical copies at the same point. In the child process, it returns 0. This means that I can now tell if I'm in the child. If fork ID is in fact 0, then this is the child process. If fork ID otherwise, I'm in the parent process. And now, instead of replacing everyone with this fairly violent exec call, I'm just going to replace the child with that. And the parent is just not going to do anything. So now what's going to happen is that we're going to have a command come in, we're going to fork, and then in the child, we're going to run the execute, but the parent will just hit the else and just loop back around. So we should be able to enter multiple commands. Let's try. ls. Yeah, it works. ls again. Cat shell.py. It works. There's one thing that's a little obnoxious right now. Well, first of all, the fork IDs are still being printed. But the other thing is that this $sign is like way up there. The reason it's way up there is that we're not waiting for the child to be done. We're splitting ourselves, the child just runs, and we immediately just go into the else, do nothing, come right back up, and print that $sign. We want to wait. And that is the final system call that we're going to use for this. We're going to use os.wait. os.wait will just wait for any child process to return. In this case, we only have one. What it returns is two things. It will return the child process ID, and it will return as well the status of the exit. And then we can just print something, just saying that a certain process returned with whatever status we were given. All right, let's try that. Exit. Boom, boom. ls. That's embarrassing. Child PID. That's the perils of live coding. All right, let's try this again. ls. It works. It actually returns, and it's a shell. It looks like a real shell. Cat shell.py. It returns. We have a little bit of extra debug printing here that we can get rid of. And this is a shell. Clear works. ls works. We can do all kinds of crazy stuff in here. We can run Python in here. and now we have a Python shell. We can do the things that, you know, Python does. From inside here, and this is kind of cool, we can run bash, and we're back within a shell in a shell. From there, we can run our shell again. Nothing's stopping us. And if we exit the shell that we just started, we're back to bash. That was started within the shell that we started. Lots of crazy things can happen over here. Another thing that we can start doing is we can actually start using text editors. Vim works fine. We can edit our shell from within our shell. This is incredible. This is really fun, very meta. And this is a shell. This is cool. What I'm trying to get across here is that this shell process is actually surprisingly simple. It is not simple because what we are doing is simple. It is complicated. We're forking it. We're replacing the entire memory contents of processes with each other. We are waiting on the other processes. It's complicated. However, all of that complexity is hidden within those three system calls: os.fork, osexec, and os.wait. All of those things are what makes this easy. It also emphasizes just how good Unix and Unix-based systems are at developing Unix. Right? Unix was mostly used for developing Unix, and this gives you a hint as to why this works so well. This is really wonderful. Before we go, I just want to implement one more feature to give you a sense of just where this can go. I want to implement the ampersand. So going into our actual bash cell, if I sleep for 2 seconds, it's just going to wait for 2 seconds and then return. If I sleep but say, please run this in the background, it just immediately returns. Nothing very exciting happens here. And I just want to do the same thing here. It's useful to be able to launch commands in the background. And so the way we do that is just by checking if the last token is the ampersand character. If it is, I don't want to wait. I'm also going to say that wait by default is true. And down here, we're only going to do the wait if we actually do want to do a wait. The last thing that we need to do, otherwise it won't quite work, and this is a little bit more subtle, is that the ampersand isn't actually an argument, and so we don't want to pass that to the exec call. And so this is kind of a hack, but we're just going to remove the last element of the tokens list, so when we call exec, it's returned. So we're still in our shell. We're going to exit this. We're going to exit the shell, and then we're going to run it again. So ls works still. Sleep2, waits 2 seconds, and it returns. Sleep2 ampersand immediately returns. It works. It now runs in the background. So this is cool, and hopefully this sort of gives you a sense of just how awesome these things are, how easy it is to develop these things, and how you can make things work relatively simply. A few things that don't work in this shell yet is the up arrow key. Right now it just prints the character. I can't go back. You've probably seen me type this a few times trying to get to previous commands in this video. A few other things that don't work is CD. If I want to CD to anything, it doesn't work. CD is actually not an executable. It's not something we can just execute. CD is sort of like a hint to the shell, being like, hey shell, I know that your current working directory is this. Can you just move yourself elsewhere, please? And so the shell that we implement would actually have to catch CD and do something appropriately with this. Finally, a few ideas for expansion. Right now, this is a good basic shell. We don't have pipes implemented. We don't have output redirection implemented. The way we do this is in the child process. We would close the file descriptors corresponding to standard input or standard output and replace them with file descriptors that actually point us to the right thing. So file descriptor 0 is always going to be our input file descriptor 1 our output, but they don't have to point to a file. They could point to anywhere. And this is really good. This allows ls or whatever thing we're executing to just not care. It's going to read from 0, it's going to write to 1. If it writes to 1 and that appears on the screen, that's great. If it appears in the input stream of another process, that's amazing. If it appears, in dev null, which is the black hole of Unix, that's fine too. It doesn't have to care about these things. And if you want to really take this further and start implementing, semicolons, which will execute different instructions in a row, or if you want to implement input redirection, or maybe a fancier feature, what you can start doing, and you might have background from 6031 that will help you do this, is actually build a grammar, parse out the abstract syntax tree, really understand what each of those nodes do. Like a pipe feeds in one to the other. Semicolon, it's sequential. You actually can build all of that, build a much more complicated shell. But these 4 lines, the os.fork, if fork ID is 0, execute else wait, is really at the core of the shell. This will keep coming back over and over again. I hope you find this to be cool, and I hope you also found this to be interesting and helpful to understand how system calls work in Unix. Thank you.